right now. So today's seminar, we have Ariel Zuñiga Reyes. He work in Oak, high altitude water Cherenkov Gamma Ray Observatory during his master in physics at the National Autonomous University of Mexico, UNAM. He is currently a third-year student in the PhD astrophysics program at UNAM as well, and he is collaborating both with DEEP 3600 and the scintillating bubble chamber. Today is going to discuss the paper that I've posted on the announcement of the seminar about the constraint done with DEEP 3600. So I'm turning my video off. Please share your screen. Can you share your slide, Ariel?
Yeah, sure.
Great. So just see if it still works. Yes, it works. So
it's okay.
I leave you the stage. Go. Thank you.
Okay. Wait. Okay, it's okay, right?
Yes, we can see the title slide.
Okay,
thanks.
Hello, everyone. Thanks for the introduction and for the opportunity to present these results here on behalf of the DEEP collaboration. Usually, direct detection experiments require different inputs in order to estimate the event rate they will see. But these inputs are related to the way we describe, for instance, the dark matter halo or the physics of the interaction process. But these models can be oversimplified, and thus important features in exclusion curve can be missed, or we can over-constrain in the parameter space. That's why in this work, we reinterpret the null result of the WIMP search in DEEP corresponding to the first year of operation using non-relativistic effective field theory. And this effective theory allows us to consider new interaction terms describing the WIMP-nucleon elastic scattering. We use different effective operators. Also, we explore specific interactions that arise from combining some of these operators. For instance, we studied the anapole, the magnetic electric dipole, and Milly charge cases. And in addition, isospin violating scenarios like isobvector and xenophobic were considered as well. All this part that I just mentioned is related to the particle physics involved. But we combine this analysis with modifications in astrophysics because we model new velocity distribution functions derived from analyzing out of equilibrium stellar debris that has been recently found in the Milky Way hail. Okay, so the goal was to have a better understanding on how the deep results could be affected if we merge the particle physics and the astrophysical uncertainties. Let me now mention the main features of the DEEP experiment. DEEP is one of the experiments in Snow Lab, specifically is placed in the cube hole. DEEP stands for a dark matter experiment using argon pool shape discrimination. Here is an illustration of the of the detector and the main components. In this sphere here is an acrylic vessel that contains around 3.3 tons of liquid argon. The inner surface was covered with a TPV wavelength shifter that helps to transform the scintillation light produced in the argon when particles interact. And then this light produced travels through different light guides and is detected by high quantum efficiency PMTs. And we process, and after that we process the signal. Also, the detector has foam filler blocks that provide insulation and shielding. And this whole setup was immersed in a water tank in order to block outside radiation like gamma rays and neutrons. The detector contains outer PMTs that work as muon sharing of beta. The pool shape discrimination is the strategy that we use in order to discriminate the nuclear recoils from electron recoils. That in our case, we are more interested in analyzing the nuclear recoils, and we classify the electron recoils as a background. The collaboration is big. We have more than 100 members from 8 countries. And this was the last, this photo is from the last collaboration meeting in Munich this year before the COVID situation. And where, as I mentioned, last year we published the results corresponding to the first year of operation, 231 live days, using this mass of liquid argon, what gave us an exposure of 758 ton day. But after applying all the codes, we don't see any WIMP-like signal. However, we provide in the paper a detailed description of the different backgrounds in the detector. And we show the power of the pool shade discrimination strategy. If you look at the left plot, you can see the region of interest in deep, and there is no event in there. And after that, we set an upper limit that is shown in the right plot, is the solid red line. And this curve what means is that we rule out all the region above this curve. This is the most sensitive limit with the liquid argon to the date. Now let me introduce the effective field theory of dark matter. This is a framework that gives us a detailed formulation, a more general way to account for a possible couplings between the dark matter and baryons. Instead of the two classical spin-independent and spin-dependent couplings, now we have 6 nuclear response functions that are described by 14 effective operators. Also in this model, the nucleus is not treated as a point-like particle, but its composite nature is reflected. I put here a table with different effective operators. The operator number 1 is the spin-independent interaction, and the operator 4 corresponds to the spin-dependent interaction. These operators are built with 4 main parameters: the dark matter nucleon, the nucleon spin, the momentum transfer, and the velocity, the component of the velocity perpendicular to the momentum transfer. I include here a check mark in order to distinguish those operators that are that can be used for an argon target. Okay, the dark matter nucleon interaction is described as a sum, is written as a sum over the 14 operators with CI denoting the coupling constant associated to the OI operator. And the operator number 2 was neglected, is neglected. Okay, as I said before, we expect that the WIMP interacts with the nucleus, and the nucleus will recoil, producing some signal that in our case is light. And in order to estimate the number of these events, we use this mathematical expression that depends on the detector features, depends on the astrophysical parameters, and also depends on the particle and nuclear physics that is related in the interaction. And I highlight here the differential cross section because it's the parameter that uses the effective field theory that I mentioned before. But now let me show the classical spin-independent cross section that is used by the direct detection experiments. As you can see, it's pretty simple. It depends on different parameters like the form factor, the velocity, the atomic mass, and so on. And following the traditional approach, we observe that the recoil spectrum depends on the WIMP mass, as you can see on the left plot. If the WIMPs are heavier, the rate will decrease as a function of the recoil energy. And also the rate is dependent on the nucleus mass. This means that if we use a heavier target, we will have a higher rate. But the cross section in the NREFT formalism is more complex. The matrix element, the amplitude matrix, is decomposed as a linear combination of these two functions multiplied, where the R function is the dark matter response. It depends on the velocity, depends on the momentum transfer, the interaction strength. However, the W function considers the nuclear response. This linear combination is presented here in terms of an isospin basis, where 0 means isoscalar and 1 means isobector. And the combination of the isobector coupling constant and isoscalar produce the coupling constants to protons and neutrons. Also, this expression have this K index that represent the six interactions plus two interference terms. I list here all briefly the meaning of the interactions, but I would like to focus on the non-zero W functions for the argon, which are the M response that describes the nucleon density inside the nucleus, the phi2 prime that is related to the angular momentum and spin of the nuclei, and favor heavier elements with holes in the orbitals. And this phi2 prime M, which is an interference term, is just the product of these two functions, responses. Well, just to show an example, this is the particle physics response functions for the M response. As you can see, it has terms proportional to 1 to the square of the velocity, a square of the momentum transfer. And essentially, we set constraints on each of these effective couplings. But we suppress subdominant terms related to higher operators like the 12 and 15. We don't consider those operators. With regards to the W nuclear response functions, where the W functions depends on the momentum transfer, also depends on the harmonic oscillator parameter. That is a function of the target that we use. And the W functions, we use the W functions provided, computed in this paper here, and they were determined for the isoscalar isobector couplings and also for the cross terms. And in this plot, I wanted to show a comparison between the Helmholtz factor and with the WM response. And we can say that both are pretty similar at low recoil energies. That is the range in which we are interested. And well, also related to the specific interactions, as I mentioned, we can have photon-mediated interactions that can be modeled in terms of these effective operators. We study four main cases. For instance, a dark matter with anapole moment, which is a linear combination of the operators 8 and 9. A dark matter with an electric dipole moment that depends on the 11 operator. A dark matter with a very small charge, also known as milli-charge. And the last case is the dark matter with a magnetic dipole moment that depends on the operator 1, 5, 4, and 6. Let me say that we don't, depending on the interaction, for instance, in the case of the anapole, we don't use the term related to the operator 9. So we just consider those operators that are available for argon. For for the isospin violation, it is common that the experiments show the results in terms of the dark matter nucleon cross-section, sigma n, and they assume isospin conservation. This means that the coupling to proton is equal to the coupling to neutron. So this is also the isoscalar, known as the isoscalar interaction. And I include here the mathematical expression for sigma n. And for the specific case of argon, we have that this element has a single main isotope, which is argon 40. Considering this an isospin conserving interaction, we just got that the sigma n is equal to sigma p. So, but this change if we have a target with multiple isotope. So I can say that an isospin violating scenario, what assumes is that the WIMPs interact differently with neutrons and protons. And this is something reasonable because if we think about it, um, the, the particular case when the couplings are equal is just a single case. So we know that the internal structure of the neutrons is different. So why don't explore these cases too? So we have now two scenarios. The case when the ratio is equal to -1, known as isobector, and the case when the ratio is equal to -0.7, that is known as the xenophobic dark matter. In this plot, I show the FC, that is a suppression factor, SC versus the ratio of couplings. The FC is a suppression factor that accounts for the loss of sensitivity when the interactions violate isospin. And I include here different targets. And as you can see, there is a value of the ratio in which the FC goes to higher values. This means that there is a cancellation between the protons and neutron couplings contribution to the cross section. But in the case of elements with multiple isotopes, the interaction is very suppressed, but is not zero. And is exactly this maximum for xenon what defines the xenophobic dark matter point at minus 0.7. Okay, until now I have talked about the particle physics. Now I want to show where enters the velocity distribution function, that is this expression parameter here. I put here an example of the velocity distribution function boosted to the Earth reference frame. This is a distribution which is normalized to 1. Just to do a quick recap, the standard halo model is the most simple model that we use in order that helps to describe the Milky Way halo. It is assumed isotropic without substructures in hydrostatic equilibrium, and also consider that the velocity distribution of the particles follows a Maxwell-Boltzmann distribution. It's also characterized by having a density profile that decreases with the square of the radius. We have the very popular density profiles in literature, like the Navarro-French-Why and Astor-Burker. And also this model is characterized by these very popular parameters like the local dark matter density, the circular speed, and escape speed. But the standard halo model is not that simple because recently new substructures have been identified in the solar neighborhood thanks to the data from the Gaia satellite. And this data has been combined with the data from the Sloan Digital Sky survey. The first substructure that I want to talk about is the Gaia sausage. Analyzing the stars of the halo, we observe that there are two main components: a metal group of stars with isotropic features, and this is associated to an ancient relaxed round halo. And a second group that is contained is a group of metal-rich stars with very high radial anisotropy. If you look at this plot here, which shows the motion of 7 million Gaia stars. This plot, the y-axis is the circular motion of the stars versus the radial motion. We can see that there is two components. The first group of stars with a circular velocity around 220 kilometers per second. This means that the stars are rotating around the Milky Way. However, below this structure, there is a group of stars with circular motion around zero. This means that the stars are not rotating, however, they are moving in very radial direction. This group of stars is they belong to this structure that was coined as a Gaia sausage because of the shape that you can see in the figure, the shape that is flattened and elongated like a sausage. And it's believed that this structure was the result of the collision between the dwarf galaxy and the Milky Way. We also consider other substructures like the S1 stream, which is a group of stars that are moving in opposite direction to the solar system at very high speeds. This is known also as the dark matter hurricane. We have this very recent discovered stream named NIX, which is this one that I close here. The shape is similar, with shape similar to a crescent moon. And this substructure was identified by using deep learning algorithms. And below you can see the sausage here. Also, we have Helm streams that the first members of this stream were discovered in the early 90s using Hipparcos proper motions. But with the data from this from Gaia, new members have been added to this stream. And the last stream is Koppelman, a group of stars that have a higher velocity, and then they are also reported in the literature. In addition, we also consider a generic model of infalling clumps. We use this in order to describe some extragalactic dark matter component that could be accreted in the Milky Way, but they are not modeled following the observer stars. Well, how we build the velocity distribution of these substructures? As I mentioned, in the star halo, we have a round halo and substructures. That's why we use the star's kinematic properties to trace potential dark matter associated to these substructures. We have these two component models with two terms. A first term with the velocity distribution of an early round dominating an early round dark halo dominating the gravitational potential in the innermost 20 kiloparsecs. And the second velocity distribution, that is the one of the substructures, characterized by the velocity dispersion tensor and the substructure mean velocity. So we also weight these terms with the dark matter mass fraction in the substructure. We assign a specific value for the substructure and the rest for the round halo. Okay, for the round halo, we use Maxwell-Boltzmann distribution, one-dimensional Gaussian. And for the substructure, for the substructure BDF, velocity distribution, we use a three-dimensional Gaussian. Okay, I add here this table that summarizes all the properties of the substructure that we consider. They were arranged in groups based on the similar effects that they have on the exclusion curves. We consider two models of the Gaia sausage, one numerical and the second analytical. And the substructures were also, I add here this level, depending on the speed of the substructure. We have the fast, the medium speed, and the slow substructures. If you look at the last column, is the dark matter fraction in this substructures, and in the case of the sausage, the fraction goes from 0 to a 70%, and in the case of the rest of the infalling clumps and streams, it goes to from 0 to 30%. And we select this range based on the review that we perform in literature. And this parameter, honestly, is still unknown. And we try to consider all there are different values reported. And so we wanted to consider all the possibilities, because for us it's important to see the effect that this parameter produce in the results. Okay, this is an example. This is a plot that shows the velocity distribution for all the substructures. The color gradient indicates how change the velocity distribution if we increase the dark matter fraction. And when the fraction is 0, we got the solid black line that corresponds to the standard Halo model BDF. And these velocity distribution are normalized to 1. If you look here, the fast substructures corresponding to the group 1, 2, and 3, most of the particles have high speed. The median speed substructures are those from the group 4 and the group 5, where most of the particles, the mean is almost the same position that the standard Halo model. And the group 6 substructures, they have most of the particles with very low speed. Okay, these are recoil energy spectra plots that consider different cases. For instance, the first is contains the rate produced by defective operators with the standard Halo model velocity distribution. And here, the most important thing that I would like to say is that those Q-dependent or momentum-dependent square operators that are the 3, the 5, and 11 operators, they tend to suppress the rate at low recoil energies. And for the second plot, where we use the spin-independent interactions or O1 operator with all the substructures, as you might notice, for those fastest substructures, they produce these bulges in the rate. The third plot is recoil energy, shows the recoil energy spectrum, but now considering 3 operators with 3 velocity distribution. We choose the operators depending on the velocity, depending on the momentum transfer, and those BDF that are the fastest and slowest from the group that we use. And the most important thing here is that the operators 8 and 11 are more affected by the substructures that the operator 1. And also we see here that for the G1 streams, the rate behave quite interesting, because for large recoil energies, the rate behave nearly constant across different energies. And the last plot shows the three operators, but with isospin cases. And it's evident here that the isoscalar interaction dominates, because the coherent enhancement with the square of the atomic mass. And for the cases where the interaction violate isospin, we see that the iso-vector decrease faster in comparison to the xenophobic case. Well, this is a plot that shows constraints on the interactions using the standard halo model velocity distribution. We show these limits for the five interactions and the isospin violating cases. And instead of using the coupling constant, we wanted to show, we wanted to parameterize the result in terms of an effective dark matter proton cross section, because people is not familiar with this kind of plot. And yeah, we show that the strongest limit is produced by the O1 interaction, spin independent, followed by the 11, 3, 8, and 5 operators. Um, in this slide, what I show is the effect of the substructures on two of the interactions, the O1 and O5. If you look at the strongest effect is produced at lower masses, where the lower dark matter kinetic energy places the maximum recoil closest to the energy threshold of the detector. And depending on the substructure, the limit, if we compare it with the standard halo model, that is the solid black line, depending on the substructure, the limits can be stronger or weaker. This operator, the O1 interaction, is constant, but this change for the O5, that depends on the square of the velocity. And, and due to this dependence, we observe that the enhancement and reduction in sensitivity is more is remarkable. And this is at higher masses. And this is a non-linear effect that we uh, haven't seen before. And this is the result of considering at the same time the particle physics and the astrophysical uncertainties. Now I want to present a different exclusion curve, but showing the impact on the substructure, and specifically how change the limit if we modify the dark matter fraction on the substructure. The plots are the cross section versus mass for the different interactions that I mentioned before. And the gradient, what shows is that how change the dark matter fraction in the substructure. And in below each plot, there is a relative difference plot that shows the relative deviation of each operator with the given substructure at the maximum value compared to the standard halo model. Okay, and you can see that for higher masses in this relative difference plot, there is a split. There is a split between the curves, but we have the O5 and O8 operators behave in a different way than the rest of the interactions. And this is because these operators are sensible to the velocity distribution that we are using. Okay, for this particular case of the sausages, they significantly weakens the sensitivity, as you can see, because they have less particles in the tail of the velocity distribution, less high speed particles in the velocity distribution. And I can say also that the O'Hara's model on the right is set stronger limits are higher masses, but this effect reverse for the case of Nesip Gaia sausage, where the the substructure produce stronger limits and lower masses. For the fastest streams corresponding to the U1 and U2 groups, they, as you can see, estrange the limit the most. And now it's more clear the fact that I mentioned before for the operator 5 and 8 and higher masses. You can see that the limit increase in relation to the rest of the operators, and there is a split in the relative difference plus that is very clear. For these substructures corresponding to the G3 and G4 groups, the effect here is marginal in comparison to the results that I showed before. And this is because these streams, this substructure has less high, they have less high speed than matter particles. So the effect is not too large. However, you can see that there is mass region where the limits are stronger and another where the limits becomes weaker for these streams, substructures. For the last group, we have that G5 streams. They have the mean close to that of the standard halo model. So the impact of the substructure is the effect is produced by the narrowing in the distribution. And as you can see for the E5 streams, the limit is reduced. And for the last, that are the slow substructures, they weaken uniformly the, the cross section, the limits, because most of the dark matter particles doesn't have enough energy to produce an observable nuclear recoil. Okay, now these are summary plots. It's a very nice way to see the simultaneous effect of all model variations. This shows upper limits and 90% confidence levels on the dark matter nucleon scattering cross section, but for three different WIMP masses, and for each substructure and isospin scenario. If you see the y-axis, we have the level for the different substructures and a level for the different isospin cases. And the y-axis, in the x-axis, what shows is the cross section. The shading of the rectangles, what shows how change the dark matter fraction in the substructure, show how change the cross section if we increase the dark matter fraction, where the light part corresponds to eta equal to 0, that is the result constrained by the standard halo model. So the vertical line here is the result that we published of the first year of operation WIMP search in deep. And I can say here that if you see the wider the rectangles is greater the impact of the substructure in the limits. So it's clear that the sausage and the G1 and G2 substructures are the ones that produce the strongest change to the results. Well, regarding the specific interactions, we obtain these limits, but now we constrain the coupling, the anapole coupling, the anapole moment coupling, the magnetic dipole, electric, and the Billy charge. This is important because in the literature, we observe that there are very few limits on these specific interactions, but for an argon target. So it's important that we provide these constraints based on experimental results. And the last, one of the last slide results is this one that shows the effect of the isospin violation. We set constraints on the O1 interaction for two experiments, the xenon 1 ton and deep, considering the isospin violating scenarios. Here, the limits level rescale were obtained using the method provided by Carlos Yaguna in this paper. This method is what uses is the result published and then computes a factor with isospin violation and then produce these results. And those limits level with NREFT use the effective field theory that I mentioned before. So the most important thing in this plot is that there is a region where a deep and argon-based experiment set a stronger limit than, than xenon, considering isospin violation. This is, in other words, if we assume isospin violation, we can observe in the parameter space that there is a mass region when an argon-based experiment set on a stronger limit than xenon 1 ton. Okay, we explore this case, but using the effective field theory, I mean the xenophobic case with the effective field theory, which is the black dashed line result. And we observe that the region increases. And this is related to the fact that the approach by Carlos Laguna, he used the Helfer factor. Well, the Xenon Wanton used the Helfer factor, but this form factor doesn't change assuming isospin violation. However, in the NREFT formalism, the form factor changed by assuming that the coupling to proton is different to the proton to neutrons. Okay, just to do some final remarks, we reanalyzed the deep data corresponding to the first year of operation. I present different upper limits on the coupling strengths of different contact interaction operators. I show isospin violating cases like isobector and xenophobic, and also the specific operators corresponding to Milly charge, magnetic, electric dipole, and anopole interactions. It was studied also the impact of the halo substructure on these operators. And the most important thing here is that we observe that V-dependent operators are especially sensitive, particularly sensitive to the velocity distribution that we use. In the case of if these stellar debris that has been found have a dark matter in there associated, the standard halo model velocity distribution should be updated because of the major effect that they could have on the direct detection results. And as I show, in some scenarios, we can get a nearly constant event rate, and this might imply for future dark matter researchers that we could extend the region of interest to higher energies, and allowing some distinguishing information in the recoil spectrum if we have a future signal. In the case of any detection, is important. We need complementarity between different targets in order to discern between all these model uncertainties. And the last is that the astrophysical, as you saw, the astrophysical and particle physics uncertainties can significantly affect how we constrain the parameter space. I want to also say that these results that I present here, you can access these results. They are available online. We publish this in Synodo repository and GitHub. And if you are interested in a code for computing the dark matter nucleon scattering rate with this effective field theory formalism, there is a code named WIMP that allows to compute this, and we use this code for our analysis. That's all I have. Thank you.
Thank you very much. Sorry for the clapping. So thank you, thank you. Are there any questions for Ariel? Okay, Chris, go ahead.
Okay, thanks, Ariel. That was really good and very thorough. So clearly the standard halo model is too simple, and using the standard halo model is very simple with purely spin dependent or spin independent. Just thinking about that is too simple.
Mhm.
What would you recommend the 2020 version of the standard halo model look like? Like, what should experiments compare to, and what operator should they compare to kind of provide a simple one plot comparison between experiments?
Mm,
Like should the Gaia sausage be considered standard in the year 2020?
yeah, for sure. We need to date the velocity distribution. That's the first thing that most of the experiment have to consider, because it's a structure that is present. And according to the simulations and different studies, this substructure, there is a high probability that has that matter associated. So the first thing is that the velocity distribution, the experiment in the process of estimating the rate, they should update this, at least consider the Gaia sausage. Also, um, I think it's important to have this broad spectra of interactions, because we don't know how the dark matter particle will interact. And in fact, in literature, I saw that there is an update of the standard halo model parameters depending on the recent observations. Um, in that paper, that they report that, for instance, the value of the local dark matter density should be updated. It's not quite right to use the 0.3. And also the circular speed is a bit higher, and also the escape speed. They show update parameters. So I think that we need to modify at least the parameters considering the recent observations. Yeah.
Thank you.
Are there any other question or comment for Ariel? How does your result compare to the model independent limits that have been worked out by some theoretician? Now I don't remember who was, maybe it was Paolo. I don't remember who, but there was a few paper about whether we can have limits that are velocity independent and taking out all the model dependent apart aside. Is it something?
Yeah, there are some studies that shows ways to determine the rate without this astrophysical dependence. And I remember a paper from Bradley Kavanagh that works on this. And yeah, that could be another option.
Have you compared your scaling to the scaling that they have done, for instance? If it's
No.
going in the same direction, okay.
No. Yeah, but that would be interesting. Mm-hmm.
Are there, and how, what is the lowest mass that, I mean, what is the range? Maybe you have said, but I missed. What is the mass range that you consider for in terms of WIMP mass? You can go down to whatever kinematically nuclear recoil is reasonable for the target, or?
Yeah, well, the energy, the threshold of the detector is sensible to recoil energies between 50 keV to 100 keV. So as you can see here,
This is related to the deep detector.
Yeah.
It's not related to the, so are there any systematic that if you go to lower energy, that are lower WIMP, lower dark matter masses, that can still account for a nuclear recoil in your target. That might be something different, for instance, not mandatory argon.
I'm not quite sure, but I know that
maybe my question is confusing. Sorry.
Yeah, I think that there is a problem when we go to lower WIMP masses because the treasure of the detector. So if you can see,
so it's related to the detector, not to the systematic on the different operator that you have seen. There is no such a thing.
Yeah, we are sensitive to masses approximately above 20 GeV or so.
Any other question or comments? If not, I don't see any hands raised in the participant. So I would like to thank Ariel again and for a great job and a nice paper. Thank you very much. And if you can send me